Hi everyone, and welcome to the first video of this channel. So today we are going to be doing my all-time favorite polynomial problem, and it comes from the 2016 AIME 1, and it is problem 11. So let's just get started with it. Again, this is my favorite polynomial problem, and we're actually going to be solving this in two ways. So in this video, I'm going to present the more cool solution that will actually make you like this problem, and well, it's definitely more beautiful than the second solution I will present. And the second solution is the more intuitive solution that you would do on the AIME. I'm going to do that in another video. So with that, let's get started. And I'm going to underline important information in the problem as we read. So let's see. P of x be a non-zero polynomial. So it's not zero, such that this equality holds. We don't know what to make of this yet, but let's just keep reading. For every real x, this may also be important, who knows? I mean, it's probably just true anyway, but we'll still underline it. And p of 2 squared is equal to p of 3. And then we want to find p of 7 halves, add the numerator with the denominator, make sure the numerator and the denominator are relatively prime. Okay. So let's see what we have. So whenever we have a polynomial problem, almost 99% of the time, what we do is we find the polynomial, because there usually is no specific way to manipulate the polynomial somehow. I don't know. So yeah, in this case, there is also really no way to manipulate the polynomial identities, or p of 2 squared is equal to p of 3, to get p of 7 halves. So what we're going to do is we're going to substitute values in for x to get maybe some information about the polynomial. So the first value we're going to substitute is x equals 1. Why 1? Well, there's a lot of negative ones in the polynomial. In general, what I'm going to try to be doing here is I'm going to try to get a 0 in there. And I see that on the left-hand side, I'm going to get a 0. So let's just see what that leads to. That leads to x equals 1, and that's 0, times p of 2, that's just the left-hand side, is equal to 3 times p of 1. The left-hand side is 0, and we get that p of 1 is 0. And now we again have to ask us, how can we apply this in finding p of x? Well, again, we are trying to find the polynomial. So what we're going to do is we're going to write that p of x has a factor of x minus 1. That is a direct consequence of p of 1 being equal to 0. Okay, so this trick worked once. Maybe it will work again. I'm going to find another value for which something will equal 0 maybe. And that value, well, the next value is 0. It's kind of a natural choice. So, if x equals 0, then we have negative 1 times p of 1 is equal to 2 times p of 0. The left-hand side from our previous equation is just 0. So we get that p of 0 is equal to 0. Okay, what does that mean? Well, that means that we should add another factor of x to our equation with p of x. So we get that p of x is equal to x minus 1 times something. We don't know what yet. Okay, so we can see that here we decreased by 1, and we got something with p of 1 in the left-hand side. Maybe we can get something with p of 0 in the left-hand side also. Let's just try negative 1, then we'll get something with p of 0 on the left-hand side. So, with that, let's do x is equal to negative 1, and that is yielding negative 2 times p of 0 is equal to 1 times p of negative 1, which yields to, well, from the previous equation, that yields to the left-hand side being equal to 0, and so we get that p of negative 1 is equal to 0. We already know the drill. We multiply by x plus 1 times something. Okay, let's try x equals negative 2. This ladder keeps working. Maybe it will work for x equals negative 2. Let's see. So x is equal to negative 2 yields negative 3 times p of negative 1 is equal to 0 times p of negative 2. Okay, so the left-hand side, that's equal to 0. The right-hand side, 0 times p of negative 2. Yeah, that's equal to 0. We get 0 equals 0, an identity that we have known since kindergarten. Nothing new. So I'm going to just write that. This is where this process stops. Right here. Okay. Well, how can we use this? What is this something? Well, it has to be another polynomial, right? Because the only thing that can multiply 2p of x, like times 3 linear factors, is a polynomial. Okay, so we have just turned this problem in p of x into a problem in this new polynomial q of x. And again, just to reiterate, q of x is p of x divided by x minus 1 times x plus 1. Okay. Which information in the problem can we use to find q of x? Well, the only thing that seems reasonable is this green identity highlighted. So what do we get? We get that, and now we just rewrite this green identity in terms of this new definition. We get that x minus 1 times x plus 1 times x plus 2 times q of x plus 1. Right? We just rewrote everything on the left-hand side in terms of this new definition. And that is equal to x plus 2 times x minus 1 times x plus 1 times q of x. And now we see a bunch of cancellations. So this x minus 1 cancels, the x's cancel, the x plus 1's cancel, the x plus 2's cancel. What do we get? We get a very important statement about q of x, and that is that q of x plus 1 is equal to q of x. What does that tell us? That tells us that q of x, well, it's a polynomial, we know that, right? And that's actually the only thing we know about q of x. But this doesn't tell us that, right? We already defined it like this. So what new information does this give? Well, q of x is periodic, right, with period 1. I mean, this is like the definition of being periodic with period 1. So we can write that down too. It's also periodic. What is, like, is there any polynomial that is also periodic? Yes, those are the constants. They're always equal to one value for all real x. They're periodic. So what does that tell us? It tells us that q of x is equal to some constant, and let's just call that constant c. Okay, so we have that. And this tells us a whole lot about our polynomial, because instead of dealing with this new polynomial q of x, we can just shove this q of x equals c equation into the definition. So let's zoom into the definition, and we're going to rewrite some things. So this is c times x minus 1 times x plus 1. And now we have transformed this problem from a problem in p of x to a problem in c. This green identity, it won't yield anything. I mean, this will just give us some more obvious identities, probably. The only thing that is actually useful to us here is this blue identity here. And it is this blue identity that will finish off the problem. And in general, when you're a bit stuck like this, you always look for stuff in the problem that you haven't used yet. In this case, our haven't used yet information is this blue identity here. So let's just rewrite this blue identity in terms of our definition for p of x. Why? We'll get an equation in c, and we can actually find c. So what does that yield? Well, that yields p of 2, which in terms of this definition is c times 1 times 2 times 3. All of that squared is equal to c times 2 times 3 times 4. So what does this yield? This yields 2 c squared times 36 is equal to 24 times c. And what does this yield? Well, after maybe some approach, I mean, you can actually cancel off the c's because c can't really be equal to 0 anyway. I'll show you why later. So actually we have two possible values for c. We have c equals 2/3 or c equals 0, right? And we can also have just found that by canceling out the c's from both sides to get c equals 2/3, or we can note that if we can't cancel c's from both sides, that means that c equals 0. That's just another approach. Or you can have just done this factoring. Either way works. So what we get is that c is equal to 2/3 or c is equal to 0. Let's deal with the c equals 0 case first. What do we get for the polynomial? We get that p of x is equal to 0. But can we have that? No. This red identity explicitly says that that is impossible. So if c equals 0, we get that p of x is both equal to 0 and not equal to 0. This is impossible, so c equals 0 is also impossible. This is a classical proof by contradiction that c equals 0 is impossible. And so we have the only value of c is equal to 2/3, and we get that our polynomial is 2/3 times x minus 1 times x plus 1. We have succeeded in finding the only polynomial in the whole entire world that satisfies the condition of the problem statement. And to me, that is truly fascinating. So what do? Well, now we just do some basic arithmetic to find p of 7/2. We plug in 7/2 for each value of x, and we get that p of 7/2 is equal to 2/3 times 5/2 times 7/2 times 9/2. This will yield a whole lot of cancellation. This cancels too, and we get that 105/4 is equal to p of 7/2. 105 and 4 are relatively prime. Their GCD is 1. This means that 105 is m, 4 is n, and this is a typical AIME ending. We add them to get 109. And we're done. So this is, once again, my favorite polynomial problem, and I truly think that this solution is beautiful. And I also think that it is really cool that there's only one polynomial in the world that satisfies the conditions of the problem statement. In the next video, I will be coming out with a more intuitive solution to this polynomial problem. Hope you enjoyed, and see you in the next video.